When the data mine finishes running, we get taken straight to this definitions page. We can also access this at any time that we want to by selecting definitions from this drop-down menu. What we see here is that there are 7 segments. Let's sort them from highest ratio to lowest ratio by clicking this column here that we're sorting on, the column heading. Now, these columns here, this column here labels each segment with a unique key. So this is just segment is called segment 2, segment 7, and so on. These columns here define each segment. So the first segment is defined as simply being those records where the age was between 15 and 25. That's a pretty simple definition. The next segment is where the age is between 25 and 80, and engine power is between 2000 and 2600. The segments looks like the segments get progressively more complex. This segment down here is defined as being where age is between 25 and 80, where the garage type is in fact garage, and where power is between 200 and 1600, and where vehicle value is between 5000 and 12,000. Now the column here shows the sum of the response variable in each segment for the 70% of records that were in the training set. So this is effectively the numerator in the ratio that we're interested in. OBS here is the denominator in the ratio, and this is the ratio itself. So this is response train divided by OBS train. For younger drivers, this ratio is 0.463, which is well above the overall average of 23.8% that we mentioned earlier. This ratio falls all the way down to 1.5% for this segment, which is older drivers with low-powered vehicles that are parked in a garage and of low-ish vehicle value. And these columns here are the same columns again, but for the validation set. So you'd expect that if these values here represent 70% of the data, and these values here represent 30% of the data, that within each segment, they would be roughly in the right proportion. So is this a good segmentation outcome? Was this the right number of segments? We measure goodness of a fit or of a segmentation by a trade-off between lift and correlation. Now, lift is the difference in the ratio between the top and the bottom segments. In this case, it's effectively the 0.463 minus the 0.118, which is equal to 0.345, conveniently summarized in this label up here. Now, we could improve the lift by simply reducing the minimum observations per segment and hence increasing the number of segments. With, say, 60 segments instead of 7, the top ratio is likely to be quite high and the bottom ratio is likely to be quite low. The problem with this is that with just so many segments, each having so little data in it, the ratios that we generate from that won't generalize well. We wouldn't have a good model in that case. To test how well the model generalizes, we need to compare the ratio on the training data with the ratio on the validation data for each segment. Recall that the validation data wasn't used in coming up with the segments at all. Now, Preddle finds the segments from the training data and then runs the validation data through these definitions to allocate each record in the validation set that we see here. If there is higher correlation between the ratios from the training data and the ratios in the validation data, then the segment definitions probably generalize well. The correlation on this data set was 0.94, Now, a correlation between about 90% and 95% is pretty good. Subject to keeping the correlation in this 0.9 to 0.95 range, usually we want to push the segmentation as hard as we can. And by that I mean have as many segments as possible to push the lift as high as possible. High lift makes the segmentation useful. High correlation makes it reliable. Being useful isn't actually useful if it's not reliable, and being highly reliable isn't actually useful if it's not if the lift isn't high enough to make it useful.